The topic latitudes and longitudes. What are latitudes? Latitudes refer to full imaginary circles running parallel to the equator. What about longitudes? Longitudes refer to imaginary half circles running from the north to the south pole. Okay, before we delve deeper into this topic, let's consider some previously learned concept you ought to be familiar with, and this is in relation to the parts of a circle. So with me here is the diagram of a circle. The first line that I've considered here is the diameter. The diameter is a line that touches the circumference at its ends and passes through the center. So this is the diameter that I'm talking about. And then the second line that I've considered here is a chord of a circle, which is a line that touches the circumference at its ends but does not pass through the center. Let's consider this to be the chord AB for the sake of our discussion. So the chord AB divides the circle into two parts. There is the part that I've shaded with the red color, and then there is the part of the circle that remains unshaded. So a chord will divide a circle into what we refer to as the segment, and therefore what I've shaded with the red color represents the minor segment, and therefore the part of the circle that remains forms the major segment. And then when I join the ends of the chord AB to the center, I'll end up getting this line and this line to be the radius of the circle. So it also divides the circle into two parts, and those parts are called sectors, and therefore the part of the circle that I've shaded with the blue lines, we refer to it as the minor sector, and therefore the part of the circle that remains unshaded becomes the major sector. What about the arc? The arc is a portion of the circumference, and therefore in relation to the ends of the chord AB, I can consider this line here being the minor portion to be the minor arc of the circle, and then this portion of a circle being the larger one to be the major arc of a circle. And then the angle subtending the minor sector at the center of a circle, we can give it theta. We can represent it with theta, and therefore the remaining angle, taking cognizance of the fact that angles in a circle add up to 360 degrees, the remaining angle here, which will represent the angle subtending the major arc, will be 360 degrees to subtract theta. Okay, let's consider the formulas that are applicable here. So as far as the sectors are concerned, I've considered that the area of the minor sector, which is the one that I've shaded with the blue lines here, the area of the minor sector will be theta divided by 360 degrees times pi r squared. That means a fraction of the area of the circle. And therefore the major sector will be the other angle, which is 360 degrees to subtract theta, divided by 360, and then to multiply by pi r squared. That means also a fraction of the area of the circle. What about the arc? I've captured here that the length of the minor arc L will be equal to theta, which is this angle here, divided by 360 degrees times 2 pi r. That means a fraction of the circumference of the circle. And therefore with the major arc it's also the same. That means the angle that is represented here divided by 360 degrees to multiply 2 pi r, which is also a fraction of the circumference of the circle. Okay, with the knowledge of the parts of a circle in mind, let's now consider the earth. In this diagram, I've captured a few lines. So there's this circle here which is 0 degrees. We refer to it as the equator. And remember, we said that latitudes are imaginary circles running parallel to the equator. So the equator itself is a latitude, and then I've also captured another latitude on the northern hemisphere and another latitude on the southern hemisphere. And then I've also captured lines that run from the North Pole to the South Pole, imaginary half circles running from the North to the South Pole. So this line here represents a longitude 0 degrees, so this is the Greenwich meridian. And then I've also captured a longitude here which is on the western side of Greenwich, and then another longitude here which is on the eastern side of Greenwich. And this leads us to these two statements. The first one, and this is in relation to great circles and small circles. We say that all longitudes and the equator are great circles, i.e. their radius r is equal to the radius of the earth. Now from our diagram, we can be in a position to see that I've captured 3 longitudes here, including the Greenwich. These are longitudes, and they tend to form semicircles since their endpoints are at the north and the southern poles, and therefore their radius is equal to the radius of the earth, which is 6370 kilometers. And also the equator, being a latitude, it's also a great circle because its radius is equal to the radius of the earth, since the earth is spherical. And then the circles in blue represents the small circles. Remember, we've said here that all latitudes except the equator are small circles. So the equator being a latitude, we've already considered it here being a great circle. So therefore, all latitudes will have a radius which is smaller than the radius of the earth, and that is why they are referred to as small circles. And how do we find the radius of a small circle? Let's consider the following. First of all, let's consider some 2 angles that are very important when you consider finding distances along the Earth's surface. So the first angle, we will assign it theta. So theta will represent the point difference. That means the difference in degrees from one point to another along the Earth's surface. For instance, in my diagram, I've captured a few points. So let's say the difference in degrees between point A and point B will be theta. And also you can even consider point B and D, that will be theta. Point B to point F, the difference in degrees, it will also be theta. Point E to point F, it will be theta, and such like. The second angle we can consider, I'll represent it with the beta, and this will represent how far in degrees our latitude is from the equator. And this is when we are considering distances, especially along a small circle. Therefore, as pertaining to the radius of a small circle or the radius of a latitude, it is found by r to be equal to capital R cos beta. And how do we arrive at this formula? Let's consider the following. Looking at my diagram again, I want us to consider this right angle triangle that I've captured here. Now this is where you represent the angle beta, where I've said it is how far in degrees a latitude is from the equator. So I'm assuming I want to find the radius of this latitude, so I'm looking for this small r here. So therefore, when I say that angle beta is how far a latitude is from the equator, I'm talking about that angle that is formed. So from where the equator is, this is the point, to where the latitude is, that is the angle that is formed. So I can capture with an arrow in that direction. So then, let's pick this triangle and see how we are going to arrive at this formula. So this is the right angle triangle here. And remember, the line from this point to this point was representing the radius. But now, since we are looking for the smaller radius, this line will be represented by the base of this right angle triangle. So it is from this point to this end. So this will serve as our small r. And then this line from this point to the circumference will be the radius, because all the lines from the center touching the circumference are the radius of the circle. So this line is the radius. I'll capture it with the capital R. And therefore, the angle that is formed here, we've agreed that it is beta. So then, using our knowledge of SOHCAHTOA, and we are looking for R, that is the base. And if this is the angle, this line here will be its adjacent. So we have the adjacent and the hypotenuse. We are going to consider the cosine of an angle. So we are going to say here that cos beta, the cos of this angle, will be equal to the adjacent, which is R, divided by the hypotenuse, which is capital R. And therefore, when you multiply by capital R on both sides of the equal sign, the R on the right side of the equal sign will cancel, and you are left with the small r to be equal to R multiplied by cos beta. And that is how we find this formula for finding the radius of a small circle. Finding distance along the Earth's surface. Now, there are two ways of finding distance that we consider here. And the first one is finding distance in kilometers. And we've got two categories. You're going to find distance in kilometers along a great circle, which is equal to theta divided by 360 times 2 pi r. And if you relate to the parts of a circle, we agreed that this is the formula for the length of the arc. And since the earth is spherical, any movement you make along the earth's surface is like you're moving along an arc. And then you can also find distance in kilometers along a small circle. Now you're going to consider the fact that that will be a latitude whose radius will be equal to r cos beta. Under this category, when we are considering speed, speed will be measured in kilometers per hour. The next category is finding distance in nautical miles. So there is finding distance in nautical miles along a great circle, which will be equal to theta times 60 degrees. And then there is finding distance in nautical miles along a small circle, where we say that distance will be equal to theta times 60 cos beta. And that cos beta is the effect of moving along a small circle, where beta is the angle formed, or the difference in degrees from where the latitude is from the equator. And in this category, speed will be measured in nautical miles per hour, also referred to as knot. Locating of points. So we consider locating points based on, first of all, considering the latitude on which the point lies, and then we consider the longitude. For instance, point A here lies on a latitude 50 degrees north, and then on a longitude 60 degrees west. So the point A here is 50 degrees north and 60 degrees west. The point B. The point B is also on a latitude 50 degrees north and then longitude 80 degrees east. So this is 50 degrees north and 80 degrees east. So the rest of the points are, as you can see, point C is on the equator, 0 degrees, and then on a longitude 60 degrees west. Point D is also on the equator, 0 degrees, and then on a longitude 80 degrees east. Point E is on a latitude 45 degrees south and on a longitude 60 degrees west. Point F is on a latitude 45 degrees south and on a longitude 60 degrees east. And that is how you locate points on the Earth's surface. Then let us consider different ways in which we find theta. Remember, we said that theta refers to the point difference. Now for this case, we are going to refer to it as the longitude difference, as we are going to find differences in degrees between one point to another as far as longitudes are concerned. When the 2 points are on the western side of Greenwich, so this is the Greenwich meridian here, 0 degrees, and then you've got 2 longitudes on the western side of it. There's the longitude 20 degrees west and there's the longitude 50 degrees west. So this is how we find the point A and B. So theta is simply found by subtracting. So we're going to have 50 degrees west to subtract 20 degrees west. So you're going to get here 30 degrees. So this is the point difference. So 30 degrees here will represent the longitude difference between those 2 points. And then when the 2 points are on either side of Greenwich, so this is the Greenwich meridian here, and then I've got a longitude on the eastern side and another longitude on the western side. So this longitude here is 45 degrees east, this longitude here is 50 degrees west. So this is where point A and point B are found. So theta here will be equal to 50 degrees plus 45 degrees. So there is 50 degrees on the western side of Greenwich, and then there is 45 degrees on the eastern side of Greenwich. When you add them together, we're going to get 95 degrees, and this represents the longitude difference between those 2 points. When the 2 points are on the eastern side of Greenwich, so this is the Greenwich meridian here, and then I've got a longitude 40 degrees east and then another longitude 80 degrees east. So the theta here will be equal to 80 degrees east to subtract 40 degrees east. And the solution here will be equal to 40 degrees, which represents the longitude difference between those 2 points. And then we can also consider 2 points that are located on the northern side of the equator and on the same longitude. For instance, point A and point B here. Point A is found on the latitude 60 degrees north and point B is found on the latitude 40 degrees north. And this is like considering the angle beta for the 2 latitudes. So latitude A is on the angle beta, which is 60 degrees north, and then point B is on the latitude beta, which is 40 degrees north. So theta, which will represent the latitude difference here, will be equal to 60 degrees north to subtract 40 degrees north, and therefore theta will be equal to 20 degrees. What about when the 2 points are on the same longitude but on either side of the equator? So for instance, this is point A found on the latitude 60 degrees north, and this is point B found on the latitude 50 degrees south. So theta here we are going to consider the beta as far as point A is concerned. So beta here will be 60 degrees north, 60 degrees north, plus beta as far as the point B is concerned, which will be 50 degrees south. So in total here we are going to find theta to represent the latitude difference between those 2 points to be equal to 110 degrees. And then the final one that we can consider is when the 2 points are located on the southern side of the equator and on the same longitude. So there is point A, which is on a latitude 20 degrees south, and then there is point B, which is on a latitude 65 degrees south. So theta will be found by considering, let's begin with the larger one. So there is the angle beta as far as the latitude of point B is concerned, which is 65 degrees, to subtract the angle beta as far as the point A is concerned, which is 20 degrees, and therefore the solution will be equal to 45 degrees, and this will represent the latitude difference between these 2 points. Let us now consider the concept of the shortest distance between 2 points. So here we can say that when you have 2 points that are on the same latitude, for instance the point A and point B, but on longitudes that are directly opposite or antipodal. By antipodal, it will mean that this angle, there is point A and point B here, and the difference in degrees between those 2 points will be equal to 180 degrees. So when 2 points are on the same latitude but on longitudes that are directly opposite or antipodal, or when theta is equal to 180 degrees, we say that the shortest distance between those 2 points will be along a circle of longitude or along a great circle through the nearest pole. For instance, here the nearest pole is the North Pole. And then if you have 2 points on either side of the Greenwich on the same latitude, let's say point B is now on a latitude 125 degrees east, and point A is on a latitude 130 degrees west, we will say that theta, which is the longitude difference, will be equal to the 130 degrees on the western side of Greenwich to add the 125 degrees on the eastern side of Greenwich, which will end up giving us 255 degrees. Now if you look at this theta, it is more than 180 degrees, and therefore with the knowledge we had considered of parts of a circle, this angle here, which is 255 degrees, will serve as the angle subtending the major arc of this latitude. So moving in this direction, it will be the longest distance. So we'll consider that the value of theta will have to be the angle that will lead us to getting the minor arc, which is this angle here, which will be equal to 360 degrees to subtract 255 degrees, which will lead us to getting 105 degrees. So moving from point A to point B in this direction will be shorter than moving from point A to point B in this other direction, taking into consideration that this is the minor arc of the latitude. Let's consider the concept of time. We know that the Earth will rotate in an anti-clockwise direction and that it takes 24 hours to make one complete rotation. Therefore, we can say that one rotation, which is 360 degrees, will be equal to 24 hours, and these hours we can change them into minutes by multiplying by 60, and therefore we ask ourselves, if 360 degrees will be equal to this number of minutes, what about 1 degree will be equal to how many minutes? And by cross multiplication we are going to have 24 multiplied by 60 and then divided by 360 degrees. So we end up getting 4 minutes. And therefore it means that 1 degree will be equal to 4 minutes. And then the Earth is divided into 24 time zones, and this is to allow places whose longitudes are very close as having the same time. So therefore, we will be in a position to say that if 1 degree will be equal to 4 minutes, what about 60 minutes will be equal to how many degrees? So on cross multiplication, I'm going to have 60 to multiply 1 and then divided by 4. So you're going to get 15 degrees. So therefore, each time zone is 15 degrees wide. And time in such a zone will be known as standard time. And that is what allows us in our country, Kenya, to have a standard time. And the local time at the Greenwich meridian is referred to as the Greenwich Mean Time, or the GMT. Therefore, all meridians or longitudes on the eastern side of Greenwich have their local time ahead of GMT, and the further you go to the east, the ahead the time. And all the meridians or longitudes west of Greenwich have their local time behind GMT, and the further you go to the west, the behind the time.